Welcome once again to the 75th edition of the virtual seminar on precision physics and fundamental symmetries. It's my pleasure to introduce Valerie Domcke, who's today's speaker. Valerie has had an illustrious career so far. She completed her PhD in DESI under the supervision of Wilfried Buchmuller. And since then, she's worked in a number of prestigious institutes, including postdocs at DESI, CISA in Trieste, the Paris Center for Cosmological Physics, and now lately at CERN, where she's a staff member in the theory department here at CERN. So Valerie's going to speak to us today on a new application of low mass axion haloscopes to search for high frequency gravitational waves. We're very glad that you could join us today. And with that, Valerie, the floor is yours. Thank you.
Yeah, thanks a lot. Thanks for the opportunity to speak here. Thanks to all of you for showing up and showing interest. So what I want to tell you about today is how we think we can recast bounds from low mass axion haloscopes to use them as gravitational wave detectors. So I realize this is an audience which, to my understanding, is largely experimental, whereas I'm a theorist. So I do my best to try and not kind of talk too much theory mumbo jumbo, but please do, in particular in the question session afterwards, please do ask questions if anything is unclear. So this is mainly work based on two articles. The first is a living review on the status of high frequency gravitational wave searches, where high frequency here means above the frequency range that we can currently probe with experiments, or above roughly the kilohertz range that LIGO can probe, so more in the direction of megahertz or gigahertz. And the second article here with my collaborators, Camillo Gastiaselli and Nick Rod, and that will be the main topic of the talk today. So the outline of today's talk, in the first part, which will be the shorter part, I want to give you a motivation why this is even an interesting thing to look for. So I will talk about possible gravitational wave sources, possible physics that we can be looking for in this frequency range. And then in the second part, I'll come to the concrete setup that we have in mind, and basically the physics behind the type of detection mechanism that we have in mind, and also kind of possible extensions of this. Okay, so to dive right in and to start with why we think high frequency gravitational waves are interesting. So gravitational waves per se are like the small perturbations of space-time, and they can be sourced in two main categories. They can be either cosmological or astrophysical. And what I call cosmological is basically anything really sourced at extremely early times in the universe, before galaxies and stars and all these things formed. And astrophysical I will call everything related to, from my point of view, the late time universe. So for the cosmological sources, this typically happens if we have some sort of violent event in the early universe. It could be some sort of phase transition, or it could be some sort of topological defects present. And this type of source typically gives us a gravitational wave background, which is isotropic, coming from all directions in the same way, spread out over many frequency bands, and it really appears to us basically as noise. So this is very similar to what you may know from the cosmic microwave background. So some isotropic noise coming from all directions, and of course the big challenge will be to distinguish this noise, which is a signal, from the instrumental noise, which is a noise. And I'll talk a little bit more in a second about the types of amplitudes, or the signal strength that we can expect, and also the frequency dependence that we can expect. One thing to emphasize is that in vanilla cosmology, meaning kind of in the standard cosmological models, in the simplest cosmological models that we have, we do not have a clear prediction for this. Or, I mean, the prediction that we have predict something which is going to be very small and very difficult to detect. There are, however, a whole lot of very well motivated extensions, basically motivated on solving some open questions in particle physics, which do predict rather large signals. So the idea behind looking for these cosmological gravitational waves is the idea of probing BSM scenarios. On the astrophysical side, what we have in mind is some localized gravitational wave source, meaning the gravitational wave is coming to us from a very specific direction because there was some event in that part of space-time. So for example, there were two black holes merging. This is what we've seen with LIGO. But also here it is important to know that in this frequency band, there's no known astrophysical sources. So also here, this is purely a search for new physics, right? So we have by no means we have any guarantee to find anything here, but if we do, it's a strong indication for new physics. And I'll show you one example in a second, which is the example of primordial black holes merging and forming these types of signals. So these types of sources have the advantage that they can in principle lead to larger signals. And so that would probably be our first target for these types of gravitational wave searches. So I have one slide on the cosmological and one slide on the astrophysical sources. So on the cosmological side, what we know simply from observation is that the amount of gravitational waves that we generate in the early universe can be at most 10% of the total radiation energy density at that time. Otherwise, we would have seen it. Otherwise, it would have modified the expansion history of our universe. And so rescaling that by the amount of energy in radiation today, we can conclude that the total energy stored in gravitational waves today relative to the total energy density of the universe today can be at most 10 to minus 6 or so. So that's an upper bound that we have from observations on the amplitude of these cosmological sources. And it's fairly easy to come up with models. I mean, you know, as a theorist, it's easy to build models, right? The hard thing is testing them. But it's fairly easy to come up with models which would actually saturate this bound. I will also give you a second number to keep in mind. So this is basically a bound on the total energy density. Now we like to, instead of quoting the energy density, we like to also use the this dimensionless parameter little h, which is basically the amplitude of the gravitational wave multiplied by some frequency dependent factor. Well, okay, let's say for now, let's say you can ask me more details later, but let's say basically this is the amplitude of the gravitational wave. It's called the characteristic strain. And at frequencies that we're going to be interested in, around 100 megahertz, this is constrained by the same bound, can be translated to a bound here, which is of the order 10 to the minus 29 or 10 to the minus 30 in that frequency range. So that's kind of going to be the target for the cosmological sources. The frequency dependence, so the very interesting thing about these types of sources is that there's a one-to-one relation between the frequency of the gravitational wave as we observe them today and the time in the history of the universe when this is sourced. And the take-home message from these formulas is that events happening at very, very early times in the universe, so a temperature, say at 10 to the 10 GeV, far beyond the reach of any collider we will ever be able to build on Earth, these kind of high temperatures can be probed by looking at high-frequency gravitational waves. And that is kind of the main interest from a cosmologist or from a theory point of view to hunt for these guys. Yeah, as I said, it's pretty easy to come up with models which actually do this. So I just give a list of models here. I don't want to go into all the details, but I give you the link again to the Living Review article, which summarizes both on the experimental side and also on the theory side what we think is the current status of the field. Now, for the astrophysical sources, I just want to give you one example, and that is the merger of light primordial black holes. So primordial black holes means these are black holes which are not formed as usual in stellar collapses or collapses of stars, but instead they are seeded by some other mechanism, and they are generated at extremely early times, even before structure formation and star formation took place. And so these primordial black holes have the advantage that their mass is a free parameter, and we can consider masses which are much lighter than the masses that we would consider if we were looking at stellar origin black holes. And so what I'm showing on this plot here is the strain, so the gravitational wave amplitude that we can hope to achieve with these primordial black holes in somewhat reasonable models as a function of the frequency. And again, I should say this is not a standard model prediction, right? I mean, generating these light primordial black holes requires a significant amount of new physics. But what I'm showing is parameter space, which is kind of not constrained by any other bounds that we have. And what this plot is showing is the event rate that you can expect if you had a detector sensitive to this frequency and sensitive to this strain sensitivity. So for example, if you had a detector here at 100 megahertz with a strain sensitivity of 10 to minus 23, right, you would expect, well, let's go down here. Let's say we have 10 to minus 24 strain sensitivity, right? Then we would expect one event per year, which is, something somewhat reasonable on the timescale of a detector. This kind of bump, this enhancement is due to as we go to smaller and smaller masses, we become sensitive to the dark matter halo of the Milky Way, as we get a local overdensity of dark matter, which in this case are the primordial black holes, which boost our signal. But the take-home message that I want you to take away from this plot is that with astrophysical signals, kind of the target range for this strain sensitivity is of the order 10 to the minus 23, 10 to the minus 24, right? Whereas for cosmological sources, our target is much lower, right? Our target was a 10 to the minus 30. So this is why kind of the more promising signal to our current understanding is to look for something like this. And here we're not looking now for a stochastic noise-like signal. Here we're really looking for an spiral-like signal, which in shape and form looks pretty much exactly like we've seen from LIGO, just shifted to a different frequency range. Okay, so that was just for the motivation, just to tell you that there is some somewhat reasonable physics, right, that we can be looking for at these high frequencies. But now, how do we go about actually looking for gravitational waves at these high frequencies? And here, what I want to show you is how we used some existing experimental limits, as well as some prospected experimental limits from low mass axion haloscopes, in particular ABRACADABRA, SHAFT, and the dark matter radio proposal, and how we can kind of basically recast these bounds into gravitational wave bounds. And then that will also give us some indication to think how you could possibly build a dedicated gravitational wave detector in this way. Okay, so to do so, what I need is basically so maybe just 1 second on this. So I'll get to it in more detail in a second. But basically, the way these type of experiments work is you have this coil here generates a strong magnetic field, which is kind of going in a torus. And in this presence of the strong magnetic field, you can you have a vertex where you kind of from the axion interacting with the strong magnetic fields generates an induced magnetic field, and that induced magnetic field is what you read out, and that's how you look for axions. Okay, so we want to do the same. We want to see how this type of an instrument, exactly the way it is built, if that will give you any sensitivity to gravitational waves. And why do we even think that could work? So the reason that we think that could work is that if you go back and you look at a classical electrodynamics textbook, then normally that will have be classical electrodynamics just in usual flat spacetime. But in the presence of gravitational wave, which is a contribute like a curvature of spacetime, so an additional, here g mu nu is the full spacetime, eta mu nu is the usual flat spacetime, and h mu nu is now a small perturbation, a tiny perturbation, right, 10 to minus order 10 to minus 20, a tiny perturbation to this flat spacetime. And now what we need to do is we need to rederive Maxwell's equations, rederive electrodynamics, now not under the usual assumption of a flat spacetime, but under the assumption that we have a flat spacetime plus a small perturbation. So we can do that. And I mean, it's basically, it's in Landau-Lifshitz textbook, but what we found is that there's a very nice way of actually writing this, which we weren't aware of beforehand, and which makes it very clear the analogy with the axion case. So what happens is we have the two Maxwell equations. We're looking at this here in the absence of any background currents. So this would normally be the homogeneous, this would be the inhomogeneous Maxwell equation. This is the homogeneous Maxwell equation. And what we see is that we get an additional term, which basically, it's not really a current, but it acts as a current in the inhomogeneous Maxwell equation. And it can be written in terms of this polarization and magnetization vector, where this polarization and magnetization vector are given by these rather lengthy expressions here. But the only thing I want you to take away here is that all of these terms are proportional, linearly proportional, both to the amplitude of the gravitational wave, h, and to either the background electric field or the background magnetic field. So what this means is that in the presence of a background electric or magnetic field, a gravitational wave will act effectively as a current, as a source in Maxwell's equations. And the source will, of course, now induce electric and magnetic fields, and it's these induced electric and magnetic fields that we want to hunt down and detect. And there's a direct analogy here with the axion case. So in the axion case, of course, you have flat spacetime, right? But what you have is you have an additional term in the Lagrangian, which couples the axion to E dot B or to FF dual. And you can write an exact same formalism, just that now this P vector and this M vector are given by these expressions here. So it's simpler because the axion is a scalar, the gravitational wave is a tensor, so we have no indices here to worry about. But again, we see that these effective source terms are proportional, of course, to the axion, proportional to the external field, and proportional to the axion-photon coupling. And precisely this analogy is what will allow us to recast basically any axion experiment, which is kind of based on this type of axion electromagnetism interaction. We can recast now in terms of a gravitational wave detector. I have a slide here which I don't want to go to in detail, but I just want to mention it because I think it's important to at least be aware of the topic, right? And the point here is that we have to be, since now we're working with gravity in curved spacetime, we have to be careful with the frame, with different possible frames that we can work in, and basically about kind of not getting ourselves tricked by the transformations that you can make in GR. And so the only thing that I want to highlight here is that there's two very common frames to use. Typically, when one talks, in particular as a theorist, when one talks about gravitational waves, one likes to work in the transverse traceless gauge, which is the frame. So it's a frame where kind of your test masses are freely falling, and you describe everything in relative to these freely falling test masses. So the freely falling test masses set the coordinates of this frame. And this frame has the advantage that the gravitational wave is described in a very simple way. But it has a disadvantage that if you now have an object which is not freely falling, because it's rigid, it's macroscopic, such as an experimental apparatus, this would now appear to be oscillating, even as just rock solid standing in your lab, right? And the reason it seems to be oscillating is because your coordinates seem to be oscillating, because your coordinates are the freely falling trajectories. And this is not a very intuitive way at all to describe any object in your lab. So instead, what you want to do if you want to describe an object in your lab, you would want to use the lab frame, right, or the proper detector frame, which is exactly what you would think it is. So you kind of use a rigid ruler to identify the coordinates in your lab frame. And this is kind of now nice to describe your experimental apparatus, but it's a bit of a mess to describe the gravitational wave. So this nice simple form that we get up here for the gravitational waves now turns into this more involved form. But this is an exact expression, and it's doable, right? So if you plug this into Mathematica, okay, it's you get larger expressions, but it's all still doable. And so we choose to work in this frame, right? And of course, you could also choose to work in the other frame. In the end, the results should be the same, but it matters that you describe both your experimental apparatus and the gravitational wave in the same frame. So you shouldn't mix frames halfway through your computation. And I emphasize this because this is kind of something which was, I think, known to some for a long time, but also kind of ignored by others also for a long time. And this is somewhat important to get the correct results. Okay, so now let's look at basically a simplified, a theorist's view of how an axion detector works. So here we have the toroidal static magnetic field. Now, in the presence of a gravitational wave, I showed you that this leads to an induced current. In the case of the axion, this induced current or this effective current would run also precisely in the circular direction. In the case of the gravitational wave, because we have the tensor structure, it's more complicated. The current has contributions in all directions, but it in particular also has a contribution which goes in this angular direction, and that is the one that we will be most interested in. Now, once we have this induced current will now, just via Lorentz force, right, it will source an induced magnetic field, right? So you can do the standard right-hand rule, see where's your induced magnetic field, and you will see that you get an induced magnetic field which is coming out through the center of the loop here. And now notice that this induced field is in a region where, at least in theory, you have zero external field, and this induced field is oscillating because it's proportional to your gravitational wave, right, which is a wave, whereas your external field is static, right? So these are kind of the two key points that you have in order to distinguish this induced field, which is going to be very small, and you want to kind of pick this up, right, without contamination from your background field, which is very large. And then you put a pickup loop in the center of your apparatus, and you measure the flux, the magnetic flux coming through this pickup loop, and that's going to be your observable at the end of the day. And so you can compute this induced flux that you get as a function of the gravitational wave frequency, which is omega, as a function of the gravitational wave amplitude, which is h cross. The cross indicates one of the two polarizations of the gravitational waves. It depends, of course, also on the value of your external magnetic field. The larger you make your field, the better. And it depends on the volume factor here. This thing is basically, it's some sort of a volume factor, where this little r is the radius of the pickup loop, the large r is the radius of the torus, and a is the width of the torus. And it depends on the angle of at which the gravitational wave hits your detector. And so now we can compare this with what we get in the axion case. So in the axion case, you can go to basically the exact same computation. This is, of course, in the literature, and you will find that in a similar way, right, the axion flux depends on the mass of the axion, which in the wave picture corresponds to the frequency of the axion. It depends on the axion photon coupling. The axion mass has basically been replaced here by the dark matter abundance, assuming that the axion is dark matter. And again, we have a volume factor which looks a bit different, but depends on the same parameter, and of course the external magnetic field. So now what we can do is we can just take the bounds, which are usually phrased in terms of GA gamma gamma, right? So which are essentially, with this formula, we can translate these bounds on the magnetic flux, and we can recast them on bounds on this magnetic flux, which is now sourced by gravitational wave instead of axions. And in this way, we can, just by comparing these two formulas, up to a caveat I will mention in a second, we can recast bounds set on GA gamma gamma as bounds on the gravitational wave amplitude h. Now, one thing that you notice when you compare these two formulas is that when you look at the volume factor here, this is basically just something which scales as length scale cubed, so radius cubed times a logarithmic correction. Whereas here you get something which scales as radius to the 5th power times omega cubed. So you get an additional omega times length scale suppression, which suppression in the sense that kind of typically you're operating these experiments in a regime where omega times r is small, so where you're kind of in the long wavelength mode of what you're looking for. So this gives you a penalty factor, but the once you've paid this penalty factor once, the interesting thing is that since you're scaling here with volume to a high power, it means that kind of as you increase your volume, right, your sensitivity to the axion photon coupling grows, but your sensitivity to the gravitational wave strain grows even much faster, right? So in terms of volume scaling, this is actually very promising. Okay, then, but actually this factor here was, to us, it was a bit surprising. We hadn't seen this coming. So we kind of tried to understand, okay, why is this happening? Why is this happening for the gravitational wave case, and why it is not happening for the axion case? And one of the things that is happening here is that when you look at the leading order contribution of this flux, so here I'm looking at basically, I'm looking at the pickup loop now, and the colors are encoding the value of the magnetic field as it flows through the pickup loop. And the blue and the red correspond to negative and positive values. So this means that if I now, and this is the leading order contribution, so if I now compute my total flux through this pickup loop, I'm performing an area integral over this entire loop, and the blue and the red parts will exactly cancel, and hence I lose my leading order contribution. This is due to the tensor structure of the gravitational wave. For the axion case, this does not happen because the axion is just a scalar, so the flux in this entire region would all be pointing in the same direction, would always have the same sign. So for the axion, it just adds up, but for the gravitational wave, due to the tensor structure, you have this cancellation effect, and hence you lose the leading order, which then gives you this omega times r cubed suppression that we saw on the previous slide. So what you can instead do is, once you realize this, you can say, oh, well, now I have a rather simple idea on how I can improve on this. I mean, rather simple set as a theorist, right? But I think this is actually a possible, really a doable thing. And that is that instead of taking a circular pickup loop, you could take a figure-8 pickup loop, like indicated here, meaning you basically take this side when you take the flux from one hemisphere, and then you take from one semicircle minus the flux of the other semicircle, right? And then again they add up again. Of course, for the gravitational wave coming from this direction, right? So for gravitational waves coming from a certain direction, you would now kind of significantly increase your sensitivity because you no longer get this cancellation effect in the leading order contribution. So that's a way how you could really get kind of a parametric improvement for searching for gravitational waves. Unfortunately, this will kill your axion signal, right? So this is maybe not what one can convince people to do. But one can do compromises, right? One can consider putting both types of loops, or one could consider, for example, doing just one single semicircle. Then you would lose a factor 2 on the axions and lose a factor 2 on the gravitational waves. But you still at least still be picking up the parametrically, you'd be picking up the leading order contributions in both cases. Okay, so then with all this in mind, we can now go and we can take the actual data from the axion haloscope. So here's the data from ABRACADABRA in this black and blue lines, and from SHAFT in gray. And these are, as I said, these are bounds on J gamma gamma as a function of the axion mass, but the axion mass has a one-to-one correspondence with the frequency. So basically, these are bounds on Ga gamma gamma as a function of frequency, which now we can directly recast as bounds on the gravitational wave strain, again, as a function of frequency, by equating the two fluxes, right? The flux for the gravitational waves and the flux for the axions. Now, there's one additional complication here, and that is the quality factor. So the axion signal comes with a very high quality factor, meaning it's oscillating in a very coherent way, right? This is kind of the assumption that we have for an axion dark matter background field. For the gravitational wave, it depends on the source. It depends, like if we're thinking of something like black hole mergers, it depends on kind of if you're observing the merger rather close to the merger time, in which case the coherence will be rather low, or if you're observing it very far from the merger time, in which case the coherence will be very good, but your signal amplitude will be very small. So how kind of this quality factor enters in your experiment really depends on the setup of the experiment. But here in the case of these axion haloscopes, what we find is that it enters with a relatively low power. So we just pay a penalty factor of the ratio of the quality factors times 1 or to the power of 1/4. But this is kind of not something that can be said in the same way that this is not true kind of for all types of gravitational wave instruments, right? It really depends. In order to do this conversion, you need to have information kind of both on the source, because that tells you the quality factor, and really on the experiment, because that tells you kind of how the quality factor enters into this conversion. But once this is understood, then you can kind of take the existing limits here from ABRACADABRA and SHAFT, or we can also take the prospects here from dark matter radio, and you can go ahead and you can plot this now as constraints on the gravitational wave strain. So this is what you see here. So the left is for the circular pickup loop. So this is kind of just taking the axion existing experiments and taking the proposals exactly as they are. And then on the right, we have it for the figure 8 pickup loop. So where we say we imagine that we can modify the pickup loop. And on the axis, you have again strain, so the gravitational wave amplitude as a function of frequency. And now what you can see here in green and purple, these are the existing limits. These are not, I mean, they actually cover some parameter space, which formally is not covered yet, though probably because simply nobody has thought about it. But like the existing limits are not terribly good, right? 10 to minus 4 for strain. If I give you a comparison, I mean, something what LIGO was seeing is at the order of 10 to minus 20 or so, roughly, right? And if you remember beforehand, you know, that the benchmark points that I was giving you were something like 10 to minus 24, 10 to minus 30. So this by itself is not terribly interesting. But I mentioned to you that we have this fantastic volume scaling, which means as we scale this up, right, as we go to the different dark matter radio proposals, right, which are these guys I was showing beforehand, then you really dramatically improve your sensitivity, and now you're really talking of reaching kind of strain sensitivity of roughly 10 to minus 18 if you manage to reach here the QCD axion line in the axion case. So if kind of these proposals are built and they kind of are performed all the way down to the QCD axion line, which is the goal, then you would kind of automatically be covering this parameter space for high frequency gravitational wave searches. Now, if you want to do a bit of more dedicated search, right, then you can do this figure 8 configuration. And here we also kind of added a fantasy experiment where we think we can even take the dark matter radio proposal and even maybe kind of make the largest conceivable detector that we think somewhat makes sense. And then we can get down to, well, 10 to minus 22 or so, roughly. Whereas the PBH signal that I was showing you earlier, assuming we kind of want to see roughly one event per year, meaning you know some reasonable order 1 number of events for the lifetime of the experiment, that would get us this purple line here. Okay, so this existing proposal that we have at the moment is not yet sufficient to actually probe the parameter space where we think we have a reasonable theory to hunt for. But it is covering parameter space, which was, you know, so far unexplored, and, you know, which is, you know, really now looking at strain sensitivities, which, you know, are on the right ballpark to actually think, okay, gravitational wave with this strain sensitivity is in principle a possibility. And in gray here, I'm showing some other proposals. In particular, and in particular, so what we see here is that these other proposals roughly reach similar sensitivities, despite, as I'll show in a second, they are really quite different proposals. So it's kind of interesting that everybody seems to be coalescing around this strain sensitivity, and we do cover some range. For example, here in this frequency range, and also down here, we could, if this happens, right, when we could cover parameter space, which is not yet covered or not yet even proposed to be covered by anything else. And I should also mention that some of these other experiments that are on here, in particular the ADMX-like experiment here, also rely on kind of recycling axion experiments as gravitational wave experiments. So I think that kind of underlines the point that, you know, this is kind of something that the ADMX type experiment is cavity based, instead of kind of having this magnetic toroidal magnetic field configuration that we have here, but it also relies on the conversion of axions into photons in the presence of a background magnetic field. So with that in mind, let me just zoom out a bit on this parameter space. So what I was talking about to you right now, right, is basically this hatched black region here, right? This is kind of where we very roughly think we could get with dark matter radio. This is a plot of a wider parameter space where on the one hand we saw the cosmological sources, right? As I mentioned, the cosmological sources are significantly harder to find than the astrophysical sources. So indeed, they are completely out of reach for this proposal, but basically also for all other proposals. This is why kind of we propose to first go for the astrophysical signals. But more importantly, what this plot is showing is it's showing also other experimental proposals. This is just 1 year older than the plot I was showing on the previous slide. The plot on the previous slide is already significantly busier. And this is precisely showing that kind of it really is development in this field. The reason I wanted to flash this plot is to show that, okay, this is really a wide range of frequency space. And there's some windows here which are still completely open. And what I also wanted to illustrate here is that the types of experiments which are being used, there's a huge spread between very small scale experiments, very large scale experiments, mechanical experiments, electromagnetic experiments, which indicates that we really have no idea if and how or what even could be the experimental technique that could be useful in this frequency range. At the moment, we don't have a single technique, which is obviously the right one, right? We don't have a single technique which in any obvious way could be scaled down to actually reach this line, which is where we really want to go. So just to give you some example, these bounds here, Alps in particular, right? But also CAST. This is basically a light shining through the wall experiment. So you have a laser pointing to a wall, and then a camera behind the wall. And the idea is that you convert the photons in your laser into axions. And then when they convert back into photons, then basically your camera would detect these photons. And the exact same thing, again, works for gravitational waves. But again, this is the synergy between axion searches and gravitational wave searches. And so you can use the ALPS experiment, particularly the ALPS-2 experiment at DESY, to look for such gravitational waves. And this is a not so small experiment anymore, right? I mean, this is using in the old Hera tunnel. But again, it uses this interplay between, or this analogy between axion physics and gravitational wave physics. On the other hand, here, just to take one example, these are these bulk acoustic wave devices. This is this purple blob here. These are centimeter-sized mechanical devices. And basically, the idea is that you excite a certain phonon excitation in these bulk acoustic wave devices. And then the gravitational wave will kind of disturb the phonon in these bulk acoustic wave devices. And again, if you have one, right, there's kind of a lot of noise sources to worry about, but you could maybe hope to build an array of these things, and in this way look for gravitational waves. And there's also, I should have put a reference, but there's really some very interesting works out on this already. And this is actually, so this is the empty boxes are proposed experiments, right? Whereas the filled boxes are actually existing experiments. So these bulk acoustic wave devices really have a ray set bound, and it's like at the order of 10 to minus 20. So this is definitely an interesting regime. So I'm mentioning this because I really think kind of there's a lot of room for creative people. And since we're looking at high frequencies, we're looking at rather small length scales, meaning we're not looking at something like the LHC, right, to discover this, but largely, with the exception of ALPS, largely we're looking at relatively small devices to sort of kind of tabletop type experiments, or these lab-based experiments in the hope to look for gravitational waves here. Okay, so with that, I come to my conclusions. So the 2 points that I wanted to make is that gravitational wave sources at high frequencies are really a very interesting window to new physics. Firstly, because in some sense, it's a background-free search, right? So of course, it's not true, right? Because you first have to make sure that what you're detecting is a gravitational wave and not something else. But once you convince yourself that what you're detecting is a gravitational waves, there's no standard model sources in this frequency range. So anything that you see is some sort of trace of new physics. It's also particularly interesting because these high frequencies translate to very early times in the universe, where the standard model of particle physics is not well tested, not well constrained. And in fact, we know that we have open questions regarding dark matter, regarding generation of the matter-antimatter symmetry. So we know that we very likely need to extend the standard model of those energies. And here we have a tool, a window to target precisely these energies. But I should also say, I mean, there's really no guarantee for any signal whatsoever, right? Nature could just also be unkind, and we could build the most fantastic experiments. And even if we reach all the way down to 10 to minus 30 in strain, even if we reach all the way down to the n bound, there's no promise of a signal here, but it's exploring possible theories. Then the other point that I wanted to make is that there's really a lot of synergy between axion searches and gravitational wave searches. And that basically this interplay that we know between axions and electrodynamics, that it has a very nice analog for gravitational waves and electrodynamics. So the presence of a gravitational wave without doing any new physics, right? This is just classical electromagnetism and classical GR. But the presence of the gravitational wave acts as an effective source term in Maxwell's equation. And you can use that to look for kind of electromagnetic effects induced by the gravitational wave. And that's one promising way, I think, to look for gravitational waves in this frequency range. Okay, and with that, I think that's what I wanted to say. And I'm very happy to answer any questions.